Hello everyone, I'm Dr. Kang. So today I'm going to talk about the Rao-Cramer inequality for variance of estimators. So the Rao-Cramer inequality is a useful theoretical result that tells us something about the lower bound of the variance of an estimator. So let's look at what the theorem says. So the Rao-Cramer inequality is about the following result. So let x1, x2 until xn be a random sample from a distribution with probability density function f of x given theta. So if y equals to some function of x1, x2 until xn is an estimator of theta, right, where the expectation of y is equal to some function of theta, then the variance of y is bounded from below by this result. So the first order derivative of g theta, taking it, squaring it, and then dividing it by n times the Fisher information with respect to f of x theta. All right, so we're going to look at the proof for this important inequality. So let's look at the proof. So for simplicity, we are going to talk about the case where x is a continuous random variable. So if in case it is a discrete random variable, so we will replace integration with summation, right? So the proof, the general outline of the proof is similar. Okay, and it's also important to note that this result only applies to so-called regular cases, right, where your probability density function, the support of the probability density function does not depend on the parameter. Like for example, if you have a normal distribution, then the support is on the real line. It doesn't depend on mu or sigma square. On the other hand, some distributions like the uniform distribution over an interval, let's say from 0 to theta, now that support depends on the parameter. So the Rao-Cramer inequality will not cover such kind of situations where the support depends on the parameter. All right. Okay. So let's start off with taking the expectation of y. Right. So the expectation of y is basically equal to this function, and it's equal to g of theta. Okay. So by definition, g of theta is therefore the multiple integral over the real lines u of x1, x2 until xn, and then multiplied by the joint PDFs of the sample, right? So this is dx1 until dxn, right? So here is the joint PDF, okay? So this part is the function that we're interested in, right? So this is merely by definition, okay? All right. Now, if we take derivative of g of theta with respect to theta, right? Suppose we want to find the theta g of theta, which is g prime theta. So we can interchange the order of integration and differentiation in this case by using Leibniz rule, right? So by applying Leibniz rule, we can have the following result, right? So here this does not depend on theta, so we have d of the theta of this joint PDF, right? Okay, dx1, dx2 until dxn. Okay, right, this is by Leibniz rule. So now we need to have a representation for this particular result. So what does this derivative of the joint PDF look like, right? How does it look like? Okay, to answer this, we will have to work with the log form, right? So let's look at the following result. So if we differentiate the log of the joint PDFs, right? So we differentiate it with respect to theta. This is the same as differentiating the sum of the log of f, right, of x theta, and we can write it as follows. The okay, right. Now, however, the left-hand side is also equal to, if we think of this as one particular function, then it will be equal to the derivative of this entire product divided by the product, right? So the idea is to look at this whole thing as some function like, say, L of theta, right? Okay, so the numerator will be the derivative of L of theta, and the denominator will be equal to just L of theta. So this gives us the result that we want, right? So the derivative of the joint PDFs is given by the sum of the derivative of the log, okay, multiplied by the joint PDF, okay? Alright, so this is the result that we want. And we simply substitute this result into the previous multiple integral, and we will get the following result. So g prime theta equals to multiple integral ux1 x2 xn, and so we replace the derivative with this result, right? Theta, then the joint PDFs, right? dx1, dx2 until dxn. Okay. Right. So we will call this equation 1. Right, and then over here we will denote this sum here, right? We'll denote z as equal to the sum of the derivative of the log of the PDFs, right? Okay. Now, let's try to find what's the expectation of z. So the expectation of z is 0, because the expectation of the derivative of the log of the dense PDF with respect to theta is 0, right? So this is a basic result that we already established. And then we want to find the variance of z, right? So the variance of z will be equal to the variance of the sum of the following, right? So this is basically n times the variance of this function. Okay, and this is equal to n times the expectation of the square okay, minus the square of the expectation, right? So the square of the expectation but then we know that the expectation of this derivative is equal to 0 because of this result here. So basically we have okay, so basically we have the following result, right? N times the expectation of the square of the derivative. So basically this means this is equal to n times the Fisher information with respect to the f of x theta, right? Okay, by definition. Okay. So now that we have established the value for the variance of z, so now we can go back and look at the, so let me clear some space here. Okay, let's clear some space here. Okay. Now, so let's look at this part here. So this is our z, right? Okay, and this part is our y, okay? So essentially we can view g prime theta as the expectation of yz because so this part is y and z, and here is their joint PDFs, right? Here's the joint PDF. So this multiple integral essentially means the expectation of y times z. And then we know that the correlation between yz is defined as the covariance of yz normalized by the product of the standard deviations for y and z, right? And by definition, the covariance of yz is equal to the expectation of the product of yz minus expectation of y, expectation of z, right, over here, sigma y, sigma z, okay? And because expectation of z is equal to 0, so this part disappears, right? So this whole part disappears, and therefore we have the expectation of yz is equal to rho of yz times sigma y, sigma z, right? Okay. And this is equal to g prime theta because the expectation of yz is g prime theta, right? Okay. Now here we can note the following, right? So our rho yz is equal to g prime theta over rearranging, we get this result, right? And then if we square this, then we square the whole thing, right? So this is basically g prime theta square over the variance of y and the variance of z, right? And then we know that so the square of the correlation is always bounded between 1 and minus 1. So the square of the correlation is bounded from above by 1, right? So then this implies that this result here is bounded by 1, okay? All right, so from here then we are almost done. Let's clear some space here. Okay, so from here we rearrange, we have the variance of y. Okay, so this is the variance of our estimator, is bounded from below by g prime theta square over the variance of z, right, which was just now found as n times I of theta. Okay, so this result here is our Rao-Cramer inequality. Okay, so the Rao-Cramer inequality says that the variance of the estimator, right, of theta is bounded from below by this result here. Okay, so the numerator depends on the function g of theta, right, and then the denominator depends on the Fisher information, okay, as well as the sample size. Right, so a very important special case here. So let's write this again. So the Rao-Cramer inequality says the following. Okay. So if g theta is equal to theta, right? So the case of unbiased, so y is unbiased for theta, then g prime theta would be equal to 1, right? So this implies that the Rao-Cramer inequality will be of this simple form, right? Okay. Okay, so that's all for the proof of the Rao-Cramer inequality. So thanks for listening.